Oh, wow. Okay. Hi, welcome to United Astronomy Clubs of New Jersey. So while people are filing in, settling down, I do want to welcome you here. We're back on site in Jenny Jump State Forest in Hope, New Jersey. Lovely day, little bit rainier earlier, but we are outside enjoying the nice weather that has been granted to us. So while people are settling down, a few things for the people online. You can check us out on our website, uacnj.org. It's where you're going to find a list of all our upcoming talks we've had in the past. That was your computer doing weird ding things. Not to be confused with Wingdings, which is a font that no one can read. But talks and information on our member clubs. Because the best way to get involved in astronomy is actually to join your local club because of ease of access, if nothing else. And all of them are usually doing great things that you can check out on various nights of the week. In addition, you can check us out on our social media pages. We have Facebook, Instagram. We got a Discord server for any of you people out there who use Discord. All great places to reach out, ask questions, and also see any special events we may have coming up in addition to our website. We also have an online store, so for people online, if you're really craving some sweet Astronomy Club merch, you can see that at store.uacnj.org. If I remembered the URL correctly, but regardless, it's on our website. Behave. Now it quiets down a little bit. All right. So, since we look to be settled, quick safety briefing before we get started for those of you who are joining us here. If you need to use the bathroom, that is the porta potty in back. It is bright blue, and in the dark, it is illuminated by red because you can't really see that it's blue when it gets dark, and it will get dark since we are in a state park. Speaking of getting dark, when we go to leave, we are using our headlights because we want to continue our streak of having no people run over or hit. We've had a streak for at least 5 years, and we'd like to keep it going. And besides that, it's no fun to get hit by a car. Trust me, I've done it. 0 out of 10. I'd like to avoid that. That being said, when we are wandering around, if we have flashlights, help us walk. Try and keep those pointed towards the ground. We don't need to accidentally blind people by performing sick flashlight rave tricks. They're very neat, just perhaps not here. So, in addition, we also have a little museum area, meteorite displays, all that fun stuff in there, along with a gift shop, which I will be manning after the presentation because they still have yet to give me the ability to be in two places at once. Once that happens, I'll take over the world. It'll be great. But until then, that's probably why they haven't allowed me to do that yet, upon second thought of that. But you're here to actually hear Paul speak, Paul Fischer. He's going to be speaking about the black hole he has in his pocket. Paul has a bachelor in engineering and chemical engineering from Stevens Institute of Technology and has worked in the environmental and chemical industries. Though always interested in celestial objects, Paul's official start in amateur astronomy was one night several years ago lying in awkward positions on his roof, freezing cold, holding a pair of binoculars. He then caught a brief clear glimpse of the Galilean moons of Jupiter and was hooked. After introductory reading that puts my to-be-reads list to shame, he purchased his first telescope and is now a active member of the Northwest Jersey Amateur Astronomers and volunteers here at UACNJ, and he's actually currently vice president. Ooh, ah. And with that, he still manages to find himself frequently outside at night, still in awkward positions, trying to get clear glimpses when the weather allows. With that, here's Paul.
Thank you, Kim. And hello, everybody. I just wanted to also mention, as part of the introduction, we are a volunteer organization, completely volunteer. No one gets paid up here. We do run on a shoestring budget, so your donations do make a difference. If you like anything you saw tonight, maybe consider a donation this evening. It would certainly help us out. Okay. I'm going to talk about I've got a hole in my pocket, and that's actually a quote from a movie. A lot of you are too young for this reference. I apologize in advance, but that is a quote from Ringo Starr, the character Ringo, in The Yellow Submarine, from the United Artists and King Features Syndicate. Okay? Some of you might remember that cartoon from way back when. And here's the Fab Four themselves. Come on, people my age. What's this right in between? In between. That's a blue meanie. That's a blue meanie from the cartoon. And they were fighting against the blue meanies, and they won. And everyone loved everyone else at the end of the movie. Cool movie. It's a quote from that movie. And here's the eponymous Yellow Submarine itself. With the Fab Four, with exactly 4 windows in the submarine. Imagine that. But that's not really what I'm here to talk about. I'm going to talk about a different hole. I've got a hole in my pocket, demystifying black holes. And it's by me, Paul Fischer. And as Kim mentioned, I'm a member of NWJAA, and I observe and volunteer here at UACNJ. All right, so who's actually got the tea on black holes? All right, not me. I'm an amateur astronomer. I'm not a professional astronomer. So I have a lot of surface knowledge. I enjoy and follow the science. But I am not a scientist myself. As Kim mentioned, I'm a chemical engineer, so I have a technical background, but not. I do not do original or any type of research on this subject. For correct information, though, come see or rent or purchase the video series "Black Holes Explained" by Alex Filipenko. He's a PhD, and it was available. At least I got it through the Great Courses 2009. So credit him with any of the good information that you see tonight, and for any mistakes, you can blame me. No problem. If there's anything that you know is wrong, you know, it's not Dr. Filipenko's problem. All right, so let's go over what we're going to go over. What is a black hole? Concerns about gravity, black hole sizes and types, how are black holes formed, what are some facts about black holes. People, sometimes it's a little bit of cognitive dissonance when we say that we have pictures of black holes. How's that possible? What happens if, you know, a rock, we'll say, falls into a black hole? What's LIGO doing with black holes? What's the LHC? Will the LHC do bad things with a black hole and doom us all here on Earth? We'll talk a little bit about Hawking radiation, HAIR, and S. And we'll talk at the end, we'll just mention really extremals, white holes, and other dimensions. We won't go into that too much. I will refer you to Dr. Filipenko and others to get further information on those. And really, any good detailed information can be found from any number of sources. So this is basically a book report on a video series I watched. Let's start with what a black hole is. A black hole is a region of space where nothing, not even life, can escape. Now, I just said a region of space. It's not a particular thing. Or it is a particular thing, however, there's more than one component to that thing. Carl Schwarzschild formalized the concept in 1916. He calculated the radius at which light could no longer escape these things. That's equal to R equals 2 gm over c squared. G is Newton's universal gravitational constant. Who's had physics? Okay, so you might be familiar with G from classic mechanics. G still exists even for other calculations. The above equation can be derived as escape velocity using Newtonian physics or from general relativity. We're going to explore a little bit about which one's correct. We're not going to go into the math too much. First of all, I don't claim to understand relativistic physics. That's beyond my scope as an amateur astronomer. However, we'll reason our way through it a little bit and try to gain a little bit of understanding why one of them's correct and one of them not so correct. Oh, there we go. So here is the anatomy of a black hole. We have in the center of this big black mass there, or that big black thing in the center there, in the center of that is a singularity. And a singularity is a place in space that all the matter of something has accumulated, and really is currently approximated as a point. Then we have the event horizon. The event horizon is actually the black portion you see here, or inside the black portion. It's a spherical space that exists around the singularity, from which light cannot, or anything else, can escape. Light is things that don't have mass are the most energetic you can get, must travel at the speed of light, and nothing can travel faster than that. So if you're trying to get away from a gravitational pull of an object, you're not going to do any better than the speed of light, and therefore you must fall into the black hole beyond this event horizon. There's the photon sphere around the event horizon, and that's where light is actually bent around the black hole. It's so close to falling in that it actually can orbit around the black hole just above the event horizon. Relativistic jets are like this, coming out of the poles of the black hole. Those come from the accretion disk, the interactions of the accretion disk with the black hole. Stuff is becoming, reaching close to relativistic speeds. Relativistic means getting close to the speed of light. So this stuff is still matter. This stuff still has weight, still has mass, but is getting accelerated very close to the speed of light, and through magnetic and other interactions gets ejected off the poles of the black hole, obviously on this side of the friendly side of the event horizon. The innermost stable orbit is just that, the inner portion here above the event horizon. And then the accretion disk is this whole bunch of stuff that is orbiting around the black hole. And you notice here in the picture, in this illustration, that it's glowing. As I said, this stuff is accelerated near the speed of light, so that stuff is very hot because it's interacting with everything else that's accreting around the black hole. bumping into it. And of course, the more things bump it together and vibrate and move, the higher energy they are, and therefore the higher temperature, and therefore they are going to be glowing. So that's important. Another feature of most black holes, or many black holes, is that a lot of them tend to have companions. Our sun is actually kind of a loner. Many suns exist in the universe where two or more suns exist in the same star system. So many times you'll see this type of scenario where we have a black hole, a stellar black hole here, with an accretion disk, and it's actually attracting material from its partner in the solar system, in its solar system. So many times you'll see a companion also in a black hole system. So again, you want to take this idea of a black hole in your mind and realize that it's this system of things and not just the singularity. A lot of people confuse black holes with the singularity. It's not. It's actually the entire system. So think of it that way. Okay, black holes are actually pretty mundane objects. They are incredibly exotic, but they behave very familiar. Oh, I'm not going to get that word tonight. They behave what we would consider in many ways normal. Black holes, unless you approach them too closely, act as any object of the same mass. If the sun were to suddenly turn into a black hole, don't worry, it's not going to. The Earth would continue to orbit around it just as it normally does. Why does it not get sucked into the black hole immediately? What's that? It's the same mass, and we have Newton described gravitational attraction to us, and that equation does not change. If it's the same mass of the Earth and the same mass of the object, it's just now a black hole instead of a sun. Nothing changed. So the same gravitational interaction is going to go on, and the Earth will continue to orbit that object as normal. Of course, if it is a black hole, it won't be giving off light the way it used to, and we'll probably feel those effects. But don't worry, none of this is not going to happen because our sun is just not going to suddenly turn into a black hole. We don't know what the material of a singularity is made of. It is called a singularity because our physics and math currently do not describe it. Although treated mathematically as a point source, some experts do not believe it's actually infinitely small. If everyone remembers back in geometry, a point is infinitely small, right? Or infinitesimally small. It doesn't have a length, width, or height. It's just a point in space. There's no length, width, or height to it. But some experts do not believe that it's actually infinitely small. We are prevented from directly observing the singularity. And I want to get this straight. Some people, again, this is sometimes a little bit of cognitive dissonance. It's not that we don't have the technology to see singularity. It's we will never be able to see the singularity of a black hole. Physics prevents us from doing it. If you put anything on the inside of the event horizon, nothing's coming back out again. Okay? That doesn't mean that we can't infer things. It doesn't mean we can't mathematically calculate it. It doesn't mean that we can't take indirect measurements. But what it does mean is that we will never directly observe a singularity of a black hole. We are prevented from doing it. All right, gravity concerns. I said there are two. There's traditional mechanics, and then there is Einstein from Newton here, and then Einstein here. is proposed special and general relativity as an explanation for how gravity works, and they don't agree. So they're going to have a little battle here. All right, Sir Isaac the classic Newton states that escape velocity can be calculated using this equation right here. And all you have to do to solve is you solve for v here. So you end up with a square root because it's squared here. You move these two over to the other side, and right here you got it. And all you need to do is to calculate it is the m's cancel, right? And you wind up with this equation. All right, there's a couple things wrong. Let's see here. Mistake with the illustration. The satellite would have a different VE than what is shown, calculated here, which is the VE at Earth's surface. All right, R for the satellite is different than R from the center of the Earth to the surface, center of the Earth to the satellite. Two different values, so not exactly correct. The VE at the Earth's surface, okay, when V is the speed of light, okay, VE equals V0 the square root of 2. Okay, so when we'll come back to that in a second. There's two issues with classical mechanics. Let's discuss the previous slide. If Newtonian physics were actually valid in this situation, all we need to do to calculate the Schwarzschild radius is to substitute c, the speed of light, into the escape velocity equation, right? However, remember that light has zero mass. Light is massless, and you cannot go faster than the speed of light, which this equation does not address at all. Right? There's no reason why this v, as long as the numbers on top are sufficiently large, there's no reason, and the r is not, or the r is extremely small, the escape velocity could be above the speed of light according to that equation. So that's wrong. Also, what happens if the speed of light here, we put c in on both sides here? We get 0 equals 0. So the equation disappears, right? We get an uninteresting equation. Yeah, I know 0 equals 0. That doesn't tell me anything. It's no longer a valid equation. So that's the two issues with classical mechanics. In the case of light, it's just not valid. So Albert the General Einstein had a remedy for this situation. And right here, we don't need words. That's how elegant Einstein's solution is. We don't need words to describe it. This mesh is a quantity called, someone who's had physics, tell me what that's representing, this funnel here around that massive object. That's space-time. Space-time. So Einstein proposed that gravity actually affects space-time. And so what happens is objects coming into the influence of the mass in the center of this depression actually follow the curvature of space from space-time and Einstein's predictions accurately affect even things traveling at the speed of light. So that's all that is the mass warps the space and time around a very massive object. All right, which ski trail? Any skiers here? Any skiers? No. Okay. Oh, okay, good. Which ski trail would you take? Would you take this one here when you're starting to learn how to ski? or maybe as you get better and better, you might go down some of the more extreme slopes. But would you go down this one here that doesn't have a bottom to it? No, no, no. So this would be the double black diamond or triple black diamond, whatever's the worst. This is the bunny slope, our sun. This one is a certain injury if you were to take that slope. Okay? And that's what's happening with a black hole. Here you have the sun. It's a very mild slope. Even though the sun is very strong, it's eating comets and stuff that gets close to it all the time, right? A white dwarf may be the same mass as the sun, but what happens is that the space around it as you get close is more warped. The slope is more drawn. It's more, the slope is higher, even though the gravity, total gravity is the same. And then if we turn the sun, say, into a neutron star, it would even be pulled further down. The slope would be more extreme as we get close to the object. The black hole, what ends up happening is that it becomes infinite. That slope is just vertical. You are going into the black hole as you get close to it. That's what that means. That slope is so high, it's just straight up and down. You're not traveling back up. All right, so Einstein's general theory of relativity explains black hole phenomena much better. He has a flawless victory. And when I say that, not only in this fake fight that we set up between Newton and Einstein, but Einstein's theories are proved over and over and over and over again. They set up experiments trying to break it on purpose, and nope, he's just been right every time. R equals 2g m over c squared. Schwarzschild was no dummy. He actually did use Einstein's general theory of relativity to calculate this escape velocity, or the radius at which an event horizon happens. All possible paths, all possible futures lead to the black hole. You're not getting away. You're just going into the black hole if you go to the make it to the other side of the event horizon. Even massless light at the universal speed limit c cannot escape. Why do I call it the universal speed limit? Because you can't go faster than it. Nothing can go faster than it. Not just light. Gravity travels at the speed of light. Energy of all sorts that's massless travel at the speed of light. In fact, you must travel at the speed of light if you don't have mass. So anything that is, any information that passes from one thing to another must travel at the speed of light. Let's go on into black hole sizes and types. So over here is black hole type. We have stellar, supermassive, intermediate. Then we have primordial and micro black holes. The color key, green means that evidence exists. Yellow means that it's theoretical. Some of the equations support the possibility of these things. However, there's no current evidence about these things existing. Stellar black holes can be several sizes larger than our sun. Oh, this is mass of, this symbol means our sun. The mass of our sun. So the size ranges of these things are the next column over. The stellar black holes go from several masses of our sun to hundreds of our times the mass of our sun. Supermassive black holes can be hundreds of thousands to billions. And intermediate black holes, 1,000 to 100,000. Those are approximate guidelines. I don't know whether that's some sort of universal agreement on there, but that's approximately where many scientists feel that those ranges lie. Where can we find them? Stellar black holes are ubiquitous. Anywhere there are stars, you can find black holes. That doesn't mean that one has to be right near you. It just means that they're spread out somewhat evenly throughout where stars are. In the center of most galaxies are where you find supermassive black holes. And intermediate black holes, candidates are in places like the center of globular clusters. And I think there was a relative report on recent research saying that they are close to confirming the first intermediate black hole in an actual globular star cluster. Primordial black holes, none are found. They're proposed. What a primordial black hole is, a black hole that formed from the Big Bang, not from stellar, supermassive, or intermediate black holes, but from the Big Bang. None have been found. It's interesting how they're looking for them. Black holes that just happen to be out there in space wandering around, very difficult to detect. The way they think they can find a primordial black hole is knowing its mass and looking for a signature of what happens when a black hole evaporates. And we'll get into black hole evaporation in a little bit. Micro black holes are just a theoretical thing at this point. There is no evidence that they exist. If they do ever form, they almost immediately evaporate. So not really, I think many people find it an interesting area of research. How are black holes formed? Stellar black holes are a stellar remnant. Supermassive black holes, what we know about them is that they accrete mass and energy. How they formed, we don't know. We don't know how supermassive and intermediate black holes, and when I say we, again, I'm an amateur astronomer, the science community does not know about how these were formed. Primordial and micro, remember that none of these are theoretical. The theoretical way that they could form primordial, gravity and phase fluctuations during the Big Bang formed the black hole. And then micro black holes, high energy particle reactions, but again, they evaporate very quickly. All right, so let's talk about stellar black holes. How do they form? This is from, the reason this slide's a different color is because I actually stole this from a presentation I do on stars. Electron degeneracy holds up white dwarfs. Particles with quantum values must stay separate, the Pauli exclusion principle. The free electrons in such a star order themselves and provide a back pressure to resist gravity. Remember, a star is a balancing act. You got fusion, highly energetic fusion pushing the material of the star outward. You have gravity of the star, of the collected material, pulling it in, and it's always a big balancing act. So what happens is when that fuel gives out, the electron degeneracy holds up. That's called a white dwarf when that happens. If the electron degeneracy isn't sufficient at just under 1.5 solar masses, the star will continue to collapse. So if electron degeneracy isn't enough, something else must hold up the star from the gravitational collapse. Neutron degeneracy holds up neutron stars. It's exactly like electron degeneracy. Neutrons are excluded from occupying like states. Neutron stars get an addition. The reason why it's a little bit stronger and why it's able to hold up an even more massive star when it runs out of fuel is that neutron stars get an additional assist from the strong force. And that it supports between 1.5 and 3 solar masses. It has to do with spin and other physics of the star itself. Beyond those opposing forces, I've got nothing, and the universe can't answer either. the star remnant will continue to collapse and then form the black hole. So that's a stellar black hole. Here's a supernova remnant that it's from, I don't know which instrument took this picture, but it's a NASA's picture, so very nice and colorful, but we can actually see the Crab Nebula in one of the telescopes when it's up in the sky. Okay, and the intermediate and the supermassive black holes, this is a reenactment from some of the actors on how accretion happens. It's as simple as that. It just eats material that fall into the gravitational influence of the black hole, will orbit, and if that escape velocity, if it doesn't achieve the escape velocity needed, then it will just fall into the black hole. All right, what real evidence of black holes do we have? Something's there, but we can't see it. X-ray source from an accretion disk of material stolen from a companion. We can see those X-ray sources. A star wobble from a companion. A missing afterglow. Those are some things that phenomenon that are happening in a system, but we can't see the object. So maybe it's a black hole. However, we get corroborating evidence also. Maybe gamma ray bursts, maybe quasars and active galaxies, maybe some sort of spectra broadening, maybe some sort of gravitational waves are detected, or maybe Einstein rings or gravitational lensing is seen. Here's an example of star wobble, how they actually do it. This is and remember we talked about the binary system, how many of these black hole systems have a companion star. Well, here is a smaller star, here is a bigger star, and we can tell, say if this is a black hole and we can't see it, we can tell that there's a black hole there because they're going around each other. And if you remember the Doppler effect, we actually get a shift in the spectra back and forth. So they observe the star system over a period of time, and they see this shift back and forth of the spectra coming from the star system. And they see that shift, and they say, aha, there's evidence that there is something else there, that this star that we can see is wobbling around or revolving around an object we can't see. Gamma ray bursts, these are very bright and can outshine the galaxies that they are located in. So we can detect those gamma ray bursts. Quasars. Quasars are the active centers, the very active centers of old galaxies. This is cosmic time. This is us now, and this is way back at the beginning of the universe. And you notice here there's a spike of quasars being identified. This side's the Big Bang, and this is us now. Sorry, I got that backwards. And you notice here that there is a spike right here after a bit of time after the Big Bang, but then it spikes and then drops off. What's happened there? Why don't we detect these quasars anymore? Well, that accretion disk, eventually the black hole in the center of a galaxy eats up everything close to it. So you see this die-off of active galactic centers in this time range after the Big Bang, which we can tell because remember, for things very far away, we're not actually looking just at the light of that system, but we're looking at the light of that system that many billions of years ago, based on how many billions of light years it is away from us. So that in this range of light years away from us is where we find quasars, where before it finished eating all the stuff next to it. Does that make sense? here's what spectral broadening is. If we're close enough to a black hole, we can actually put a telescope on this side of the accretion disk of the black hole, and then on this side of the accretion disk of the black hole. And look at these arrows. This arrow's going this way. This arrow's going this way. They're spinning in the same direction, obviously, but one is spinning towards us, the other is spinning away from us. So we're going to get a shift in the Doppler effect. This one's going to be blue shifted. This one's going to be red shifted. All right, so one's going to sound like it's coming closer to us, like a train coming closer to us. Remember, it goes and it changes frequency in sound. Well, that's what's happening to the light. The light doesn't make any sound, but it's doing the same thing. There's a change in the frequency, in the tone, in the light spectra coming. One's coming towards us, the other's going away, and we can see that double peak form in the spectra. So this is not real data. This is what real data looks like. And so you need professional astronomers who can make heads or tails of these various peaks and all that type of stuff. What might be in the way? What causes extinction? What might be sources that are not part of the data set? So you need a group of scientists and some sophisticated analysis to actually get relatively clean graphs that look somewhat similar to that theoretical situation there. So that brings us to this question here. Just want to reiterate there, that's corroborating evidence. So black holes, since we can't necessarily observe them directly, we have that idea that there might be a black hole there because something's missing that should be there, some sort of gravitational reaction we're seeing. However, there's nothing there. So we need some of the corroborating evidence we saw here in order to verify that a black hole might exist there. So again, we can't observe them directly necessarily. So why are these pictures of black holes here? That's Messier 87. Messier 87 is taken by the Event Horizon Telescope. It's the high frequency radio interferometry. It's in Virgo. It's in the Virgo cluster, and it's the Virgo galaxy. It's 5.35 million light years away, and this particular black hole is a supermassive black hole that has the mass of 6.5 billion suns. 6.5 billion suns went into this black hole. It's 24 billion miles across. That's a pretty big black hole. That's Messier 87. This is Sagittarius A star, which you might recognize as, whose black hole is that? Ours, the Milky Way galaxy's black hole. So right here is Sagittarius A and Messier 87. So are those real? Yeah. What is this a picture of around here? What do you think? If you saw the previous slides, what do you think that that region there is? Yes, sir. Yeah, it's the accretion disk. Very good. Now, why did we? These things are randomly oriented in space. Why does it always look like a full donut to us? Say it again. Well, we have a telescope pointing towards it, but it could be this way, oriented this way to us, right? The galaxy could be oriented this way or this way. The object could be oriented this way or this way or this way, right? It's space, right? It doesn't have to be facing us directly. What's happening there? It's not a view from the top because we can't move our camera. Our camera's going to be on Earth. Yes, sir. Yes. Say again. I'm still not picking it up. One more time, loudly. Light bending, exactly correct. What's happening is, again, light gets bent around these objects. So the light that might be on the other side of that object gets actually bent around the object towards us. It actually gets bent in any direction, but some of it gets bent towards us, and so we can see the accretion disk around, the very energetic accretion disk around the black hole. And let's hope this works. Up, I'm not getting any sound here. There's supposed to be sound. This is Sagittarius A star. This is all actual photography as we zoom in. There's very cool music to this. Well, but you'll have to trust me on that. We're getting closer and closer. There it is. Closer and closer to the center of our galaxy.
It helps when you press the button.
Zooming in on it. And I want you to look at this bright spot right here that's flashing. Those are actual photographs still. Now, this is an illustration. That's a star going around that blinking thing. And here it is. That's a star getting distorted and pulled around the supermassive black hole at the center of our galaxy. We have actual pictures of that happening. What's going to whip a star around like that, right? Something like a supermassive black hole. So we have pictures of that. That took like, I forget what it was, but something like 14 years to gather that data of those things zipping around the black hole like that. That's really cool stuff. And it's a picture. It's a video. We did that. It exists. Oops. What happens if, you know, something falls in? In the case of stellar black holes, spaghettification. Smaller black holes, you get drawn out. The tidal forces get so steep, happening at the different parts of the black, or the black hole again is a point source, so your head gets pulled at a different gravity than your feet, than your shoulders, and you get drawn out and squashed if you were to fall in. If a rock were to fall in, same thing would happen. Anything that falls in, that would happen to. In the case of super massive black holes, you are still so far away from the singularity once you fall through the event horizon. Again, they're very massive, so the gravity is huge, huge, huge. The gravitational slope lines are not that distorted yet. So you don't actually necessarily, if you were to fall in or a rock were to fall in, whatever falls in doesn't actually necessarily even feel it once you move past the event horizon. So that's a little creepy, right? There's a point in space where you might be moving through and the black hole, you're definitely going to fall in it and you don't even know. That's a little creepy, right? So supermassive black holes are interesting. Maybe you come into contact with a highly, maybe you'd also, if something were to fall in, maybe it does come into the contact with the highly energetic accreting matter, and that wouldn't be a good day for anybody. And then you'd experience time dilation effects. Matter from objects in a black hole, gravity fields will appear to slow down from an outside observer and eventually freeze in time. So as the whatever falls into the black hole, all of a sudden it just stops. And it stays there and gets dimmer and dimmer and dimmer and dimmer forever. All right, so what happens if we had some sort of magical device that we could get information back from falling into a black hole? It might look like this. It says, what if, have you ever wondered what it'd be like to fly into a black hole? Of course, this can only happen if magic was real. That's that distortion of space and time happening around it. Look at that. You can see the entire universe in front of you. The whole thing, even what's behind you. And that was created with a physics model. All right, so a little bit of mathematical magic, because we don't have real magic to rely on. Oop. This is where you can see those things. So NASA has these visualization viewers and things like that. So go visit NASA and look for some visualization tools. They'll help you. All right, so let's talk about LIGO. What's LIGO? LIGO is the Laser Interferometer Gravitational Wave Observatory, measuring gravity waves, right? It's a joint venture between California Institute of Technology and Massachusetts Institute of Technology. It detects gravity waves from distant interactions of massive objects, neutron stars and bigger. Neutron stars and black holes, 2 neutron stars, 2 black holes, that type of thing. It detects there's 2 of them. It's in Hanford, Washington, and Livingston, Louisiana. There's 2 of them, so you can corroborate the fact that an event happens, because if it's going to happen in the galaxy, certainly it would happen in both interferometer, with the 2 laser interferometers. It would happen in both interferometers at the same time. The first detection that was verified happened on August 17th, 2017, and so far detected, now this was more than a year ago I put this presentation again, so it's probably even more now, but 83 black hole mergers, 2 neutron star mergers, 3 neutron star black hole mergers, and 2 mystery mergers, which is cool because that means, hey, something happened there that we're not really sure of, so there might be some more science there that we can figure out. This is the one of the units itself. This is the building with instrumentation and where both legs. So you can see these are at a perfect 90-degree angle. They are 4 kilometers in length. And just so you know how accurate, if you think you're figuring out how a 1/16 of a inch on a ruler, what that looks like, this can figure out the length of 4 kilometers to the width of a proton. So very sensitive instruments. And this is what they're detecting. When 2 objects interact gravitationally that are massive, they give off these gravity waves. And just so you're aware, we talked about how Einstein's predictions get verified over and over again. Well, right here is a Einstein prediction, and we've actually measured a bunch of them at this point. So again, he's just been right very often. The LHC, the Large Hadron Collider, will it do bad things with micro black holes? Some people think I would have came from the chemical industry at points in my career. Um, we do what's called a HAZOP. Anyone out there who works have done HAZOPs before? All right, hazard operability study. You before you do anything that could have bad consequences if things go wrong, you go through this safety review where you list everything that could go wrong. You list all the variables, all those type of things, and then you step through all the errors that could happen, and you can say what's the worst case, and then you try to fix things that look like they could be likely and catastrophic, that could end up hurting somebody or the environment if you go through this step by step and figure this out. Well, someone sat down with the Large Hadron Collider and it said, oh, I would hate to be responsible for this particular HAZOP. What happens if we were to create a micro black hole in this device and were to accidentally destroy the Earth? That's a pretty significant oopsie. And so they actually did look into this a little bit to see whether that would happen. CERN stands for the Council European of the Nuclear Research. It's in French, so that's why it's CERN. It's in Meyrin, Switzerland. I'm not pronouncing that right, I'm sure. Near Geneva and on the border with France. The world's largest and most powerful particle accelerator, conducting multiple particle physics experiments. It's 17 miles long and is 50 to 175 meters underground, depending upon topography. It directs two beams of protons accelerated to 99.9999991% the speed of light to collide with each other. Collisions with a nominal energy of 13 tera electron volts. And it July 4th, 2012, you might have heard about finding the Higgs boson. They announced the discovery of the Higgs-like particle. That was one of its most major accomplishments. So this art, we showed you one impressive instrument. Here's another one. So this is a map of the area. This instrument's so large you have to put it on a map to see it. So this is not the Large Hadron Collider. This is the pre-accelerator that feeds into the Large Hadron Collider, which is this circle. So a big portion of this, it's so big it doesn't even fit on this map. It's a big instrument. This is the inside, or a small section of the inside. Okay, so let's go into LHC safety. According to the well-established properties of gravity described by Einstein's relativity, it is impossible for microscopic black holes to be produced at the LHC. That's CERN, the safety LHC. So the energies and the way that these particles interact just is not enough to produce microscopic black holes. So what happens if something goes wrong, and you did anyway? CERN and Professor Filipenko also point out micro black holes would evaporate in tiny fractions of a second after they form, and even if they did not evaporate. So we're already two things of physics that we would have to break in order for them to be a problem. The third thing, even with a factor of safety of many magnitudes, that's like 100, 1,000, 10,000 times, even with a factor of that a safety factor of that much, a micro black hole that is somehow stable could not accrete matter quickly enough that we would ever be concerned for the lifetime of the planet. It's just so small, it would never eat enough mass to be a danger to the planet. So micro black holes will never cause an issue because physics don't allow them in the first place, and then finally they're too small to do anything anyway. Did I say, wait, what? At one point I did say black holes evaporate. All black holes evaporate. So let's talk about Hawking radiation, hair, and S. This is how microscopic and other black holes evaporate, by Hawking radiation. If you know anything about vacuum pressure, you know that particles can be spontaneously created in the universe. It borrows a piece of energy from the universe, and the particle and the antiparticle, say an electron and a positron, get formed simultaneously. They will then almost immediately clash together and destroy themselves, releasing that energy back to the universe. So it's a net energy neutral event, but it happens. Particles fluctuate all the time. When you get down to the really weird and small world of particles. However, on the event horizon, nothing can get away from a black hole if you go on the event horizon. So right on the event horizon of the black hole, if you one of these vacuum fluctuations happen, one particle may fall into the black hole, but the other one escaped from the black hole. And that's what Stephen Hawking, theorized would happen. That's Hawking radiation. He won a Nobel Prize for that. And it is considered something that happens. So in this case, instead of the particle that ended up not destroying itself, giving energy back, instead of it destroying itself and giving the energy back to the universe, the black hole consumes some of it, and some of it is released, thereby releasing some of the energy from the black hole. In a sense, it's getting the energy from that creation instead of from the universe at large, from the black hole itself. And so as this happens and particles fall one way and one goes the other way, the black hole that is not accreting anything anymore evaporates. You need a lot of these events in order for that to happen. So it would take trillions of years for massive black holes to disappear that way. What does hair have to do it? John Archibald Wheeler is credited with the phrase black holes have no hair. It means black holes only have the observable property of mass, spin, and charge. You could put anything in there. Something burning really hot, something very cold, something very dense, something gaseous, something solid. Doesn't matter what it is. You put it in there, it all ends up with a black hole that has only mass, spin, and charge. No hair means there is no other information available. It just gets in there and gets mixed up, and whatever fell in there, you have no idea. They are the ultimate expression of entropy, and that's what the S is. S is entropy. The infinite states of matter and energy is reduced to a frighteningly homogeneous blend of stuff. Again, it has no hair, no information is retained. It just, the black hole has these three properties, and that's it. But is the information truly lost? Scientists hate this because information's not supposed to be destroyed in the universe. Maybe not. There is a proposed hologram layer of Planck length above the event horizon where information is retained. This has implications about how we perceive information in the world. You might have heard of this hologram theory about black holes. Some people have proposed that we are a hologram on what we perceive as reality is actually a hologram on the surface, the surface of the length above the event horizon of a black hole. Dr. Filipenko also talks about extremals. These are just mathematical oddities that physicists use to calculate the boundaries of what might be possible. They put in black holes with no spin, with high spin, no charge, high charge. It's really the theoretical physicists' analog of let's open it up and see what this puppy can do when you get a new car. But they do it with math, and they do it about black holes. They bind the problem to understand it better. They set boundaries by proposing these various extreme things. White holes. Is there another end to a black hole? Are they possible? Could they be stable? Could something travel through them? And then finally, what are the implications if we do find micro black holes? Would their fluctuations of gravity imply other dimensions? Not in a spooky, another realm, Twilight Zone type of way, but you have X, Y, and Z everyone's familiar with. Another bunch of like Q, R, and S. Do we have a Q, R, and S that we can't even detect because we are 3D objects ourselves? To end this, I do highly recommend Black Holes Are Explained by Dr. Filipenko. Please, if you're interested, do get that video series, and that's a good start. And of course, there are many other sources to understand black holes better. So that's it. Everyone join an astronomy club and stay safe.
All right. Thank you, Paul, for another great presentation. So we are going to be having a question and answer session. But before I get into that, because I know a couple of you snuck in, apparently I'll get farther away from that. A couple of you snuck in during the presentation, so you guys get to also enjoy the safety briefing. If you need to use the restroom, that is the porta potty in the back. It is illuminated by red for ease of finding. We also have a little museum area with like a meteorite display and a gift shop as well. I'll be manning that after question and answer sessions. It looks like we have at least one telescope open. It is in the shed with the roll-off roof. We do have volunteers manning various things, and feel free to ask them questions. When we go to leave, we are using our headlights. We do not want to get run over. We do not want to see anyone get run over. Getting run over is just far too much paperwork, and no one needs those medical bills. In addition, if we are wandering around with any sort of flashlight, I do ask that you keep those pointed towards the ground. We don't need to accidentally blind people if we do not need to. Alright, so for how question and answers are going to work, for anyone here, you're going to raise your hand and wave it about until I come bring you the microphone, because the people online might actually like to hear your question, because chances are if you have that question, someone else also has it, but might be too shy to ask. For the people online, because we are live streaming this on Twitch and YouTube, you guys just get to type in chat. You got the easy job. And I ask those questions on my mobile device. So we're going to start off with an online question. What do you think is more likely, that will resolve the mystery of what happens at the singularity through new physics, or that will find out that black holes actually don't have singularities in them?
Yeah, I don't know. I mean, the singularity, the definition of it might change, but we're sure that that mass exists because it is affecting the space around it predictably according to the theory of general relativity. So I don't think that we're going to suddenly discover nothing there. And it may end up being something that actually has width, length, and height, or it may be something else, but there's definitely something there. So I don't think that we're just going to discover that there's nothing inside a black hole. The other one you said is that we're going to, what was the first part?
Figure out what happens at the singularity through new physics.
Through new physics. I think we are constantly making strides in physics, especially particle physics, and we are making strides to maybe universal definitions of things in physics. So I think that's more likely than, but you'd have to ask a physicist exactly what that might be. I wouldn't know. I'm not as smart as those people are. So maybe that's a great question for an actual physicist.
And to quote a very popular TV show, Doctor Who, physics, 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 physics.
Physics does rule what happens everywhere in the universe. It's difficult to get away from because it's everywhere.
Right, was there a question out here? Keep in mind, I'm kind of night blind because I've been staring at a bright mobile device. Anyone? Bueller?
Just speak up if you have it. If not, don't worry about it.
So our next online question. Are there any other situations apart from the area around a black hole that matter will reach relativistic velocities?
Yes, we've achieved it here on Earth, right? We went into the speeds. What was that? We were down to like it was 100,000th of a percentage, or was it more? It might be a millionth of a percentage of the speed of light. We were very close to it here on Earth in a particle accelerator. Enough energy, if there is enough of an energetic event, then yes, certainly particles can be accelerated to near the speed of light. Anything with mass, however, cannot actually attain the speed of light. But that close to the speed of light is considered a relativistic speed.
Right, and for anyone who is curious, apparently they did some scientific Google searching, and they also provided, and if you need, here's a cheat sheet. Neutron stars can also have accretion disks, and also pulsars emit particles at relativistic velocities.
Yes.
And there's other situations, but those pop out as mostly similar.
The way our planet was formed was by accretion. So anything with gravity can have accretion.
And Ariana, yes, I also agree that the rate at which our paychecks leave our bank accounts to pay the bills is approaching relativistic speeds.
That is true, unfortunately.
All right. Our next online question. Paul has an exclusion principle. What is he excluding?
Not me.
Not mosquitoes, because I've been getting eaten.
Not me. The particle physics is we didn't get into too much of it. I did do some a similar reading and video, learning on some things in particle physics. Particle physics is really cool, and it's even more mind-bending than black holes are. So if you really want to go down a deep wormhole, then start looking into particle physics.
All right, questions out here? Ooh, we got one.
Hi, my question's sort of hypothetical, but if a black hole were to enter our solar system unexpectedly, what would the global response be? Like, what would our best next course of action be in any preventative measures we could take? And how soon would we realize, like, if a black hole was approaching our solar system?
I imagine we would begin to see perturbations, changes in the orbits of various known objects in the solar system. So we would probably detect it that way.
And also, the most likely reaction would probably be
There is a saying that we would bend over and kiss something, and there's not much necessarily that we could do about smaller objects like asteroids and things like that. We have enough advance warning. They are small enough that we could put a little mass near them, and over time change the orbit of that object so that in the vastness of space it would miss us by a small margin. But however, in the vastness of space, a small margin can be very large, and we would be comfortable nudging it in that way and having it miss us. Unfortunately, black holes are extremely massive, and getting something close to it is problematic for reasons we went into already. So if we were to try to put something in close orbit around a black hole, that wouldn't necessarily change anything. I don't know that we would have a strategy to do anything. So we might be in trouble if a black hole were. However, if you have seen space movies where a spaceship is flying in between asteroids and things like that, remember that the distance between objects in space are incredibly large. Our own asteroid belt, the distance in between, average distance in between asteroids is 600,000 miles. You can't even see the next most likely the next asteroid close to you if you happen to be at an asteroid. Okay, so
they're likely to get hit by space debris trying to leave Earth.
So it would have to be a really unlucky coincidence that a black hole were to come near us. That is not to say that the probability is zero, but the probability is probably very small.
All right, our next online question is a complicated one. So, Bravo, if I'm saying this wrong, please correct me. The fact that we can derive Hawking radiation from combining quantum mechanics, general relativity, and thermodynamics, does this support the internal consistency of a black hole theory? Because you don't have to ever observe Hawking radiation directly.
Yeah, we do not have currently direct evidence of Hawking radiation. It remains theoretical at this point. However, many physicists agree that it is currently our best theory about what's happening. Second of all, in these extreme objects is where the various models that we use, general relativity, particle physics, these various branches of physics, that's where these ideas break down in these extreme examples. And so that's why we are looking for a universal physical, theory to encapsulate all of physics. We don't have one. So we're picking and choosing models that best describe the system, but we don't have an overall model to describe everything in the universe yet. And physicists are working on that.
All right, online chat. If you have any last minute questions, do get those in. Were there any last minute questions out here?
It is still raining, so unfortunately I don't think we'll be able to open scopes to see anything.
I know the roof is rolled off at least, so here's
Ken's braver than
question.
I am. It is raining.
Yeah, so I was just wondering, what speed do black holes travel, and what influences how they travel?
Yeah, black holes everything is moving. Everything is moving. It is constantly moving, and space itself is expanding, and everything is moving away from everything else. And there is actually probably no such thing as standing still in the entirety of the universe. So everything is moving away from everything else, and black holes, just like any other massive object, get pushed around by other things that have gravity. So other gravitational interactions. And remember, groups of things can have gravity. A galaxy can have gravity. So a supermassive black hole can get pulled by the supermassive black hole and the gravity of a galaxy next to it. So it's still subject to the laws of gravity. So that's what can accelerate a black hole. Something else massive next to it. And even small things will affect its gravity, but of course it'll have a diminishingly small effect on it. The smaller the mass that object is that affects it. So it is subject to acceleration, just like everything else in the universe. And do remember again, though, that space itself is expanding and all distant galaxies are moving away from us, and that is universally true for any massive object.
All right, and it looks like the last online question is, do we have an idea of how higher spatial dimensions, where the laws of physics may change, would affect black holes?
Dr. Filipenko does go into some diagrams about theoretically traveling through wormholes, if they even exist, or if they're stable enough to exist, and explores n-dimensional space that is required if one travels through a white hole, and or if micro black holes exist. He does, but I will. That's some really sophisticated stuff that I barely understood myself. I'm going to even say I probably didn't understand it the right way, and I will leave the expert, Dr. Filipenko, and his colleagues, of course, anyone who is studying the same phenomenon, who's an expert at such things. I would save it for them to explain that much better than I ever could.
Right, and with that, I do want to thank you, Paul, again for another great presentation. Thank you, everyone here who has joined us, and thank you, everyone online. If you wouldn't mind, do remember to hit those like, subscribe, follow buttons so you get notified when we go live next. And also, it helps us get our love of science and astronomy out to as many people as possible, and they're completely free actions.
Sorry, everyone. I shut down the light before. Maybe I should have. I apologize.
Admittedly, it's
But
very dark.
thank you, everyone.
All right, and clearer skies than we've been having, and good night. Wow, that is the sun.
We don't want to get like water spots on the lenses or anything like that.